So in chapter 2, lesson 3, we get into something that Lewis Carroll describes here. I want you to see if you can figure out what he's describing from this quote from a book called Symbolic Logic. Lewis Carroll, that's Alice in the Looking Glass, I think, and probably some other ones. What is he describing when he says, the power to detect fallacies and to tear to pieces flimsy, illogical arguments, which you will so continually encounter in books, in newspapers, in speeches, and which so easily delude those who have never taken the trouble to master this fascinating art. Try it. That is all I ask of you. What do you think it is that he's describing when he says it allows you to tear to pieces flimsy, illogical arguments? Something that you're going to run into all the time. People are going to claim something's true and not really have proof. And you're not going to be able to detect it if you don't master this fascinating art. What is it? Did you guess? Did you guess deductive reasoning? That's what it is. The ability to think logically, to use things that you know are true to figure out other things that you know are true, and thus prove or disprove what some people are saying. Well, we're going to look at deductive reasoning from a kind of a strange point of view. Rube Goldberg. I don't know if you've ever heard of this guy. This is a stamp that was created in honor of Rube Goldberg. There's his picture. He's a cartoonist of comically involved contrivances, designated very complicated inventions or machines to perform a seemingly simple operation. Maybe you've seen some of these before. Another dictionary says this. Deviously complex and impractical is a huge part of this whole thing. I have 3 links here for you to follow when you're watching this. I'd encourage you. They're pretty fun. I don't know what will happen on the video if I try it. Let's see what happens. Let's not. Take a minute. You may get wrapped up in it. This one takes a little longer. This one's short. This one is pretty cool. But they all represent the idea of Rube Goldberg. So what is he doing here? Rube Goldberg has invented a machine to sharpen his pencil. There it is. So how does this work? Well, you open window A and you fly a kite B. When the kite flies, it pulls on string C, which opens the gate on D. It allows these, what are those? Moths? Yeah, moths. The moths escape from the cage there, and they eat this coat. The coat gets lighter, which allows the shoe to come down and depress the lever on the power, which turns on the oven, the iron, which then burns the cloth material, creates smoke, which goes up the tree, which wakes up this opossum, so he gets scared from the smoke. He jumps into the basket. The basket goes down, lifts the cage off the top of the woodpecker, who then pecks the pencil and sharpens it. He puts the knife there in case the woodpecker is on strike or something like that. He can't work. Very strange. There are a number of these. This one is how to take your picture. This guy at A is trying to take his picture. So what does he do? He sits on this cushion, this whoopee cushion, air cushion, and it shoots some air out, and it blows this ice boat across the block of ice, taking the cigar piece held in hand D to pop the balloon E, which makes the dictator think he's getting assassinated, so he falls backwards onto this bulb, which then flashes the camera and takes your picture. Deviously complicated for something very simple. Each step here you'll notice is A, B, C, D, E, F, G, and so on. Here's another one. I get a little too carried away with some of these. Looks like he's trying to get his back scratched, right? How does he do that? Well, the smoking lamp here makes the fire department think there's a fire, so they spray water into the house. The man feeling the water thinks, oh, it's raining, so he reaches up and grabs his umbrella, pulling the string, lifting this little lever here, which drops this heavy ball, which is attached to the hammer then, which smacks against this metal, making noise, waking the baby. So the dog has to rock the cradle back and forth, and the hand is attached to that and scratches the man's back. And here you see that whole description. I should have stopped, but there's one more here. This one is to help the man remember to mail his letter. Maybe you can see it. Let's see, the hook pushes the boot, which kicks the football, which goes into the basket. Looks like that's going to pull the watering can, which goes onto his coat, which I think makes it shrink. So the coat shrinks, pulling this rope, which opens the cage, and I think that is a bird that goes out to eat the worm, which pulls down this little note, rolled up note, which says, hey, don't forget to mail the letter. And then he pulls out the letter and puts it in the box. So why look at these crazy fun contraptions when we're dealing with deductive reasoning? Well, it comes down to this man right here, Aristotle, famous Greek. It's something known as a syllogism, which he developed as a method to help think logically. So what is a syllogism? This is a good definition to keep track of. It's an argument. Now, this is not a fight. This is not two people fighting. An argument is simply a process of reasoning logically. So it's an argument of the form. Now, we've learned how to read this. Try to read that for yourself before I do. Maybe press pause, see what you come up with. Did you come up with this? If A is true, then B is true. If B is true, then C is true. Therefore, if A is true, then C has to be true. Or A implies B, B implies C, therefore A implies C. We have names for this. This right here is a syllogism. And by the way, I could tell you this right away. Instead of writing the word therefore, you can use 3 dots. Those are round dots, no matter what they look like. 3 dots to represent the word therefore. I think that comes up a little later. Aristotle had names for the parts of these. That first conditional statement is called the major premise, what we're starting with, which leads you to a minor premise, which then ultimately leads to the conclusion of the syllogism. Now, please don't get confused the fact that we've got this same word conclusion that we used in a conditional statement. Remember, this hypothesis leads to what? This conclusion. That conclusion then becomes the new hypothesis, leading to another conclusion. So we have that word conclusion in each statement, but here we also have the word conclusion as the last part of a syllogism. We are going to run into some today where there's more than one minor premise. That's okay. Please note then that the conclusion of the major premise becomes the what? Right, the hypothesis of the next premise. We're going to see that on some of these problems here. So in this first one, here's the conditional statement. If you slip on the ice, then your foot hits the paddle. So Rube Goldberg invention here. So there's the hypothesis, and there's the conclusion. Now we take that conclusion and make it the new hypothesis. If your foot hits the paddle, then your finger lowers near the turtle. Okay, so you're trying to keep from hurting yourself on the ice, but we're just going to take those two conditionals. Take a look at those. So what follows from that? Well, now remember, we could call this one A. If A is true, then B is true. And then we take that, make it the new hypothesis. If B is true, then C is true. So anybody have the last one. It's going to be A implies, or if A is true, then C has to be true. You got the wording? Therefore, if you slip on the ice, the finger lowers near the turtle. So then A implies C. So knowing that this happens and this happens lets us know for sure that this last one happens. So let's see if you could make one up here. If you drive to, now if your alarm doesn't go off, then try to fill something in there and then come back. What'd you come up with? How about this? If your alarm doesn't go off, then you wake up late. If you wake up late, then you are tardy for class. Therefore, if your alarm doesn't go off, you are tardy for class. We just proved a theorem that if your alarm doesn't go off, you're tardy for class. How about this one? Try this. If you drive too fast, then what'd you go with? You get caught speeding? Okay. How would the next statement start? If you get caught speeding, you have to start with that last conclusion. Then you get a ticket. So then what is the conclusion, the last statement? Got it? If you drive too fast, then you get a ticket. So when this is done in class, I'd ask you and your partner to create your own syllogism. Why don't you pause and give it a try, see what you come up with. So hopefully you gave that an effort and you're back. So here's, what's his name again? Aristotle. And what was his argument, his logical argument? The syllogism. Let's say he meets Leonhard Euler and he tries to create an Euler diagram for his syllogism. What would it look like? Please pause and try to write out what that would look like. Hope you did it. Hope you went through the exercise. Here's what mine looks like. If A is true, then B is true. So there's my hypothesis. There's my conclusion. Now I'm going to take that conclusion and I'm going to make that my major premise, by the way. I'm going to make that the new hypothesis, inside C the new conclusion, my minor premise. So what is my conclusion? Did you do this one? That would work. I don't even know if you'd need the B. I think it would be equally clear if you said, therefore, if A is true, then C has to be true. But I think this makes it fairly clear. So Aristotle, a syllogism, meets Leonhard Euler in his Euler diagrams. Looking at this crazy one here, it's a Goldberg contraption to wipe your mouth off when you spill some soup on it. Give me some of the arguments that are listed below. In other words, conditional statements. Well, I could start right in here with E. If a parrot jumps after the cracker, then the perch tilts. That would be an argument. The next one in order would be, if the perch tilts, then the seeds get upset. So I could make a new theorem then that said, if the parrot jumps on the cracker, then the seeds get upset or spill. There are any number of those arguments in there, and we could represent them this way. If A is true, then B is true. If B is true, then C is true, and so on through this whole thing. And you'll notice that in every case, the conclusion of any one premise becomes the hypothesis of the next premise, from which it follows, what's the last thing that could be written about this set of arguments, these premises? Therefore, if A happens, then N must happen. And that then is a new theorem that you've proven, because we've based it on things that are true, that have actually happened. So the Rube Goldberg conclusion from that contraption would be what in words? It would be, if he raises the spoon to his mouth, then he wipes off his chin. The napkin will wipe his chin. When you're using a syllogism, you're using deductive reasoning in something called a direct proof. We're going to later talk about something called an indirect proof, but for now, a direct proof. Remember, deductive reasoning, you need to use already accepted facts, and it leads you to a new conclusion. So through our Rube Goldberg inventions there, each of the steps was already accepted. We'd use that to prove another accepted fact and another one, and eventually we arrived at a new conclusion. So each of the premises in the syllogism were already accepted facts. And eventually, I've used this word a couple of times now today, those premises lead you to a new conclusion. They lead you to a theorem. So again, looking back at Aristotle's syllogism, we have an accepted fact, we have another already accepted fact, leads us to a conclusion which now is our new theorem. So remember, when you use a direct proof, oh yeah, this is something a little different. I want you to keep this in mind. If the premises are true and the logic is valid, in other words, correct order, A implies B, B implies C, then the conclusion that you reach must be true. But what if the premises are false, but the logic is still valid? You still go A implies B, B implies C. Therefore, well, the conclusion, not necessarily false, but it might be false. And the same is true if you use true premises. Notice here, we used false premises, and your conclusion might be false. Here we can use true premises, but if the logic is not valid, we don't go A implies B, B implies C. And if we don't use correct, valid logic, then the conclusion might be false. Let's see if we can find some examples. If a figure is a square, then it has 4 right angles. Okay? If a figure has 4 right angles, then it is a rectangle. Okay? Therefore, if a figure is a square, then it is a rectangle. So think about that a minute. What can you tell me about the premises, the first 2 steps? Are they true? If it's a square, yeah, that's true. If it has 4 right angles, then it's, well, that's true. So if the premises are true, what about our logic? Well, A, I guess I'll write it in there. A, it's a square, 4 right angles B. 4 right angles B implies rectangle C. Therefore, figure is a square. A implies rectangle C. Yes, the logic is valid, so the conclusion absolutely has to be true. If a figure is a square, then it's a rectangle. Oops. Yeah, absolutely. How about this one? If a machine is a computer, it has a CPU. Is that true? Yeah, that's what computers are. So A implies B. If a machine has a CPU, oh yeah, we used B here, that's good. It can do millions of calculations in a second. That's a C. Conclusion, if a machine is a computer, yeah, we brought A down here, then it can do millions of calculations in 1 second. Premises are true, logic is valid, conclusion has to be true. Seems like a routine, a pattern, is it always? If a creature is a bird, then it has feathers and wings. If it has feathers and wings, then it can fly. Therefore, if a creature is a bird, I'm bringing the A from up above, then it can fly. Hopefully, as you were going through this, you had, wait a minute. What's the problem here? Well, that second premise is false, isn't it? It's true that if a creature's a bird, it has feathers and wings. But just because it has feathers and wings doesn't mean it can fly. Therefore, if a creature is a bird, then it can fly. So what happens? We have a false premise. The logic is valid, A, B, B, C, A, C, but the conclusion in this case is false. Wrong premise led us to a false conclusion. Here's another one. If a figure is a rectangle, A, then it has 4 right angles, B. So far, so good. If a figure has 4 right angles, B, then it is a square, C. 4 right angles, then it is a square. Therefore, if a figure is a rectangle, A, then it is a square, C. The logic looks good, but you see, again, the second premise is false. Just because it has 4 right angles there doesn't mean that it's a square. So again, the logic is good, the premises are wrong, we have a false conclusion. I think I've got one more here for you, maybe 2. If a plant is green, then it has chlorophyll. So green, chlorophyll, B. If the plant is not green, oh, so in this case, it's not A. Looks like we're doing what? If this is the original, the second one does not have so that is, did you get it? It's the inverse, not B. Therefore, if a plant is green, A, it does not have chlorophyll, not B. Or in this case, we could almost call it C because it's a third new thing. So what happens? The premises are true. If a plant is green, it has chlorophyll. If it's not green, it does not have chlorophyll. Premises are true, but our logic is faulty. It's all messed up. So therefore, our conclusion is false. So it may be true, it may be false. Here's one more. If a shape is a triangle, then it's a square. Not. If it's a square, it has 3 sides. Not. Therefore, if a shape is a triangle, then it has 3 sides. Whoa, that's weird. Triangle, square, square, 3 sides. Therefore, triangle, 3 sides. Weird. Both premises are false. The logic is valid, and the conclusion ends up being true. Kind of strange. So just a review again. If the premises are true and the logic is valid, the conclusion must be true. But as we saw in several examples, if the premises are false, even if the logic is valid, then the conclusion might be false. And it could even happen the premises might be true, but if the argument's not valid, the conclusion might be false, but we actually had one where it was true. All right, that's the lesson for Chapter 2, Lesson 3. We'll move on to the questions. So Chapter 2, Lesson 3, the problem sets. Let's get going on these. So we've got an A, B, and C up there, and that may look familiar. We just did syllogisms that have A's and B's and C's in them. Write 2 premises that you can use in a syllogism. So how would that go? So remember, if A, then B. If B, then C. That would be your major and your minor premise. Once you have them, they want the conclusion as a conditional statement, and then write the pattern in terms of A, B, and C. So think about the way Aristotle did it. We move over to some Euler diagrams dealing with syllogisms. So look at the picture, and you're supposed to write out the syllogism. So you're going to have 3 lines, right? 2 premises and a conclusion. And then a couple of questions about them. These questions are not just random. They want you to look at the pictures. Look at the Euler diagrams and answer them with that in mind. This is a cool statement by Aristotle. He said, a statement about how you can argue correctly yet arrive at a false conclusion. In other words, you can have A implies B, B implies C, therefore A implies C, but have A imply C be wrong. And here's how that happens. Admit one ridiculous premise, and the rest follows. In other words, if you have one of the premises that are wrong, your conclusion might be wrong. Might be right, but it might be wrong. So let's take a look at these. Consider this argument. If you live at the South Pole, you live in the Antarctic. If you live in the Antarctic, you live where it's cold. If you live where it's cold, you see a lot of penguins. Therefore, if you live at the South Pole, you see a lot of penguins. The logic seems pretty good there. A implies B, B implies C, and so on. A lot of times it's important to look through and think about what's given before you look at the question. So what part of the second premise, this is the second premise, what part of that premise matches the conclusion of the first premise? So the conclusion of the first one, you live in the Antarctic, what part of this matches that? Well, it's the hypothesis. And then a couple more. What part of the second premise matches the hypothesis of the third? Starting with A implies B to represent the first premise, so writing A implies B, represent the entire argument in symbols. So A implies B, B implies C, and so on. And don't forget the conclusion, the entire argument, premises and conclusion. Somewhere in there, there's a ridiculous or false premise, which allows you to end up with something that's ridiculous. What does the fact that one premise is false indicate about the conclusion of the argument? Don't overstate it now. Think about that. Think about what we talked about in the lesson. So here's another one. And from here on, the author gets kind of fun. See if you can catch the fun. So if Spaulding is in the jungle, there are too many cheetahs. If there are too many cheetahs, Captain Spaulding can't play cards. What conclusion would follow? In other words, here's your major premise, here's your minor premise. What conclusion could you write? And then a question about it. If the two premises are true, does it follow that the conclusion must be true? Did you catch the fun in here? Maybe we'll talk about it in class. Just a reminder from the lesson. If the premises are true and you have valid logic, the conclusion's got to be true, like that last one. If the premises are false, even if the logic is valid, you might have a false conclusion. And even if the premises are true, if you're not using valid logic, your conclusion might be false. Here's another fun one. If NASA launched some cows into space, they would be put into low Earth orbit. If some cows were put into low Earth orbit, they would be the herd shot around the world. What conclusion? And what is a statement called that is proved from already accepted premises? You're going to have to look back on the lesson for that one. Again, there's a funness in that one. See if you can catch it. And another one. This one's a little bit trickier because you'll notice they don't have it listed right in a row here. You're going to have to be a little bit more careful on this one. If you take a plane, you take a plane. Here's go to the airport, and there's go to the airport. So you see the order's kind of mixed up. You're going to have to be a little bit careful in lining these up. The colors on there are intended to help you out a little bit. So copy them, rearrange them in a logical order. You don't have to rewrite the order here if you don't want to. What I said is wrong. Just do just what it says. Copy them, get them in the right order. What's the theorem that they prove? He's talking about what's the last line going to say. What's that conclusion? You won't know that until you get them in the right order. Another fun one. This one, these complicated even more. At least on this one, all the hypotheses were first. You see that? Here, there's an if here. The hypothesis is partway through. Here it's at the beginning, and here it's partway through again. What I suggest is that you rewrite them with the if at the front. But it's up to you. You need to get them in the right order. write them in if-then form, rearrange them, and try to figure out what that conclusion would be. So add that conclusion. All right, this section, they've got a theorem that you're trying to prove right here. So you have to work through this, and what they've done is they've left out part of it. So here's a premise, there's a premise, here's another premise, and eventually you end up with this theorem. Now if you think about it, a theorem starts with the first hypothesis and ends with the very last conclusion. So if two hungry vultures took an airplane, they would want to take along some food. There's the conclusion. That becomes the new hypothesis. If they would want to take along some food, how does this conditional statement end? Well, look at the next premise, and that'll help you. So you've got this one that requires you to do that. Here's another one, a theorem with a missing statement. And there's a little section about some dice here. I don't think I assigned this. This is probably a sticky credit one. So I'm going to let you work through that one on your own. And here's some thinking involved with it. If it is a die, then the sum of the numbers is that. So I took that one and I put it in an order that looks more like a syllogism, with conditional statements lined up in a logical order. This one I enjoy a lot, and really I'm only interested in which box would you pull one marble out of. So here's what it is. 2 red marbles, 1 box, 2 white marbles, and 1 box of red and a white marble. The labels are wrong. In other words, this does not have a red and white marble. It might have 2 reds, it might have 2 whites, but it doesn't have 1 red and 1 white. Same idea here. It doesn't have 2 reds. It's 2 whites or 1 red and 1 white, and same problem here. You may choose just 1 box, open it to see 1 marble. Really all I'm interested in is which box would you choose, and explaining why. Now he asks you some questions through here. Suppose you opened the box labeled here and you saw a red marble. Now he asks you some questions about that. You can do those if you want. That's fine. He's just trying to help you get around to the answer, which this set of pictures here may or may not help you. So what if we open this box here? If I pick a red, what does that tell you? If I get a white, what does that tell you? Suppose we go here and take, what happens if we draw a red? What if we get a white? Or suppose we go to this box. What if you get a red? What if you get a white? That's the thinking you probably need to follow. Here's another proof with some questions about it. Copy the figure, try it, and you'll see he's got some syllogisms. If this is true, then this is true. If this is true, then this is true. And a few more here. Make several copies. Can you draw any conclusions about whether this game will end in a win or a draw? And then finally, a set 3, some sticky credit. Word ladder. Here's an example. You go from cold to warm. You can only change 1 letter at a time. So here the L to an R to get the word cord. O to A for card. C to W for ward. D to M for warm. So he was able to go from cold to warm in 5 steps. So they give you a couple of shots here. Oh, there you see the letter changes. Trying to take those 2 and change them. And I end with a mind trap. If you want to think that one through. So some deductive reasoning. All right. Work them through. Bring your questions.